Welcome to the second lesson of our Physics O-Level series. Today's chapter is Forces and Motion. These are the segments of this chapter. So without further ado, let's start off with speed and velocity. First, let's understand what speed is. Speed is the rate at which an object or person moves, expressed as the distance covered per unit of time. The equation for speed is this. Speed is equal to distance upon time, and in symbols we write it as v is equal to s upon t. S represents distance, t time, and v speed. Just like I made a triangle for the density equation, I have a triangle here again for this equation as well. We can use this triangle to rearrange the equation to find some other value. For example, if I want to find the distance using this equation, I would simply hide the s, and what I get is speed into time. So if I multiply speed with time, I will get distance. And if I divide speed with distance, I will get time. And if I divide distance with time, I will get speed. So this is the equation for speed. And of course, if distance is measured in meters and time in seconds, speed is measured in meters per second. For example, if a car moves 90 meters in 3 seconds, its average speed is 30 meters per second. We divided 90 by 3 and what we get is 30 meters per second, which is the speed of the car. Now remember, we always say average speed because on most journeys the speed of a car varies, so the actual speed at any moment is usually different from the speed we have measured. That is why we call it average. To find an actual speed, you need to discover how far the car moves in the shortest time you can measure. For example, if a car moves 0.20 meters in 0.01 seconds, then the speed is 20 meters per second. But maybe the speed will change into something different. If the car is accelerating, the speed would increase after a second or so. So the speed varies. That's why whenever we are measuring speed like this using this equation, we always call it an average speed. The best method to find an actual speed is by using graphs, distance time graphs and speed time graphs. So we're going to read about graphs in another segment of this chapter. But for now, let's stick with speed. So now that we've understood the equation of speed, let's do some questions related to it so that we can understand how we are going to use this equation in questions. So here we have a question. A cyclist completed a 1500 meter stage of a race in 37.5 seconds. What was her average speed? So in this question, we are given the distance and the time, which are both used to measure speed. So the right and organized way of doing an equation is this. First, we write down what we know and what we want to know. So we know the distance, which is 1500 meters, and the time, which is 37.5 seconds. And speed is unknown at the moment. The second step is to write the equation and substitute the values. So this is the speed is equal to distance upon time equation. Now in this equation, we substitute values, which that is, instead of writing distance, we write the distance we are given and write the time we are given. Then we divide these two values and find the speed. So then we write it like this. Our answer is supposed to be in a sentence. The cyclist had an average speed of 40 meters per second. Don't forget to write the units. They are very important. Whenever we answer a question, we always put it in a sentence that the cyclist had an average speed of 40 meters per second. So this is how we use this equation to answer a question. Now let's answer a different type of question. The table shows information about 3 cars traveling on a motorway. This is the table. Now the questions are, which car is traveling the fastest and which car is traveling the slowest? So let's take a look at this table first. Vehicle A has a distance covered 80 kilometers in 50 minutes. Now, to find out which car is traveling the fastest, we're going to write down our speed distance time equation and divide the distance with its time. Each car will have its own speed, and the car which has the greatest speed is traveling the fastest, and the car which has the lowest speed is traveling the slowest. So let's do this right now. 80 divided by 50 and we get 1.6. So 1.6 meter per second is the speed of car A. Now we're going to divide 72 by 50 to find the speed of car B. The speed of car B is 1.44 meter per second. 85 divided by 50 is 1.7 meters per second. So now, which car is traveling the fastest? Of course, car C. And which car is traveling the slowest? Car B. Now, this was very simple. We have to use this equation, divide the distance with time, and find the speed of a car. So now, let's move ahead on to another question. So this is a complicated question. Let me read it out. A spacecraft is orbiting the Earth at a steady speed of 8 kilometers per second. How long will it take to complete a single orbit of a distance of 40,000 kilometers? Use the correct units. Okay, so the units that this question has used are not correct. As you can see, 8 kilometers per second is not the correct unit. We always use meter per second. But if they have given us the distance in 8 kilometers per second, our job is to convert it into meters per second, because the question specifically says that we have to use the correct units. The distance is also given in kilometers, so we have to convert it in meters. Now we have understood conversion of units from the previous chapter. We can convert these units easily. So 8 kilometers per second, we have to convert 8 kilometers into meters. Now we're converting a given unit back into its base unit. And what is the conversion factor that is going to be applied over here? Of course, 1 kilometer is equal to 1000 meters. So we are going to multiply 8 by 1000 to get the answer in meters per second. And so we get 8000 meters per second. Now the distance of 40,000 kilometers, we're going to convert this kilometers into meters as well. So we're going to multiply the given value by 1000 to get the answer, which is this. It's got many zeros, so I'm not really willing to read it out. Anyways, so now we have the values in correct units. Now they asked us for the time. First we write down what we know and what we want to know, which we have done so. And now we're going to write the equation and substitute the values. Now the equation has become this. Before it was something like this. We just rearrange the equation. So time is equal to speed upon distance. So how do we rearrange the equation? This is the equation. And what do we want to find now? We want to find the time. So when we hide the time in this triangle, we get distance upon speed. So distance upon speed is equal to time. Let's go ahead on to our question and rearrange the equation. So this is what our equation will look like now. Now we're going to substitute the values and divide them. And the answer is, we're going to write it in a sentence. The spacecraft will take 5,000 seconds to complete an orbit. So this is how we use the equation to solve questions. Now that we've understood this and we've practiced this, make sure you practice it as much as you can, because the more you practice, the better you get at it. And the easier it will be for you to understand it. So now that we've understood speed and the equation of speed, we can move ahead on to understanding velocity. Now, most people confuse velocity with speed. They think they are the same things, but actually they are not. Velocity means the speed of something and its direction of travel. So in other words, what we are trying to say here is that velocity is a vector quantity and speed is a scalar quantity. By scalar quantities, we mean the physical quantities which only have magnitudes but no direction. By vector quantities, we mean the physical quantities which have magnitudes as well as a direction of travel. So speed is a scalar quantity. It has just a magnitude and no direction. But velocity means the speed of something as well as its direction of travel. Velocity is the speed of something, but it also has the direction of travel. For example, a cyclist might have a velocity of 10 meters per second due east. So this is how we write velocity. On paper, this velocity can be shown using an arrow. And for motion in a straight line, you can use a plus sign or a minus sign to indicate direction. So a plus sign would mean to the right and a minus sign would mean to the left. Plus 10 meters per second would mean velocity of 10 meters per second to the right. And minus 10 meters per second would mean velocity of 10 meters per second to the left. The plus 10 meters per second can also be written as just 10 meters per second. No need to write the plus sign because it would mean the same thing. But of course, when we are saying that something is due left, we would have to put a minus sign. So this is velocity. Here we are explaining vector quantities and scalar quantities. Quantities such as velocity, which have direction as well as a magnitude, are called vectors. And those which only have a magnitude, example speed, are called scalars. So this is pretty simple. Velocity is also almost the same thing as speed because it is measured in meter per second as well, except for that what is different in velocity is that it has direction as well. So whenever we are writing a velocity down, we either make an arrow or add a plus or minus sign to indicate direction. Now that we've understood velocity, we can move ahead on to understanding acceleration. So something is accelerating if its velocity is changing. Acceleration is calculated like this. Acceleration is basically a changing velocity. Something is accelerating if its velocity is changing. So average acceleration is equal to change in velocity upon time taken. This is the equation we use to calculate acceleration. In symbols, we have it as A is equal to delta V upon delta T. By delta, we mean change in. Delta V means change in velocity and delta T means change in time. So we can make a triangle of this as well. All we have to do is place the change in velocity on the top and average acceleration and time taken at the bottom. So if we want to find the change in velocity, we can just multiply average acceleration with time taken to find it. If we want to find the time taken, we divide change in velocity by average acceleration. So this is how we do it. For example, if a car increases its velocity from 0 to 12 meters per second in 4 seconds, the average acceleration would be equal to 12 divided by 4 is equal to 3 meters per second square. Note that the acceleration is measured in meter per second square. This 2 means square. So acceleration is also a vector quantity. Just like velocity, it can also be shown using an arrow. Alternatively, a plus sign or minus sign can be used to indicate whether the velocity is increasing or decreasing. Now remember, don't confuse these plus signs with the plus signs we use for velocity. For velocity, we use the plus signs to indicate direction. Plus means to the right and minus means to the left. But this is the case of velocity. With acceleration, the plus sign will mean the velocity increasing. So in acceleration, the plus sign means that the velocity is increasing, which means that the speed is also increasing. So the object is speeding up. And the minus signs mean that the velocity is decreasing, which means that it is slowing down. The plus and minus signs do not tell us the direction. A negative acceleration is called a deceleration or retardation, which means when an object is slowing down. A uniform acceleration means a constant acceleration, which means that the rate at which the object is accelerating is constant. Say for example, it is accelerating by 3 meters per second every second. So the velocity is increasing by 3 meters per second every second. So the acceleration is constant if it is increasing by 3 meters per second every second. If it is not constant, then it would not increase, always not increase by 3 meters per second every second. It sometimes may be 2 meters per second, sometimes 4, sometimes 3. So the acceleration is not constant. Here we have a problem. A question, in other words. The car is gaining 3 meters per second of velocity every second. So in 5 seconds, it gains an extra 15 meters per second on top of its original 12 meters per second. Therefore, its final velocity is 27 meters per second. So, the result is worked out like this. Final velocity is equal to original velocity plus the extra velocity, which is equal to acceleration divided by time. So this equation also works for retardation. So if a car has a retardation of 3 meters per second square, you can treat this as an acceleration of minus 3 meters per second square. By minus, we would understand that it is a retardation or deceleration, in other words. So now that we've understood acceleration, the equation of acceleration, negative acceleration, uniform acceleration, and that acceleration is a vector quantity, we can move ahead on to understanding distance time graphs and speed time graphs. First, let's understand distance time graphs. Graphs can be useful when studying motion. So, a car is traveling along a straight road away from a marker post. The car's distance from the post is measured every second. The charts and graphs show 4 different examples of what the car's motion might be. So here we have the first graph. So a graph like this shows steady speed. So when the graph is a straight line, this is a distance time graph. A distance time graph is different from a speed time graph. So if a distance time graph is a straight line like this, it represents steady speed because the distance is increasing at a constant rate with the time. So the speed is steady, so the speed is not changing at all. It is neither accelerating nor decelerating. Then we have a graph which shows acceleration. So this graph doesn't have a steady speed because you can see the distance is increasing and not in a constant rate. Before it was in a constant rate. But now the distance is increasing more and more. Slowly and gradually, and it is becoming faster. So the car is accelerating. With this type of curve shows that the speed of the car is changing. Then we have the car decelerating, and this is also not a steady speed. Of course, if a car is decelerating, its speed is changing. So it also has a curvy graph. Then we have the car stopped. This is when the distance remains the same but the time increases. So the time is passing by but the distance isn't changing at all. So this means that the car has stopped. It is not moving at all. So on a distance time graph, the gradient of the line is numerically equal to the speed. Numerically equal means that when we divide distance by time, we get speed. So we can only find the speed of a graph which has a steady speed. So the speed is not changing this graph. If the speed is changing, we can't find out the speed. We can only find it out of 1 second or microsecond. So what we do is that divide the distance covered in time. So the car has traveled total 11 seconds. And the distance it has traveled in 11 seconds is 75 meters. 75 meters is the distance it has traveled in 11 seconds. So when we divide the two values, distance with time, we get the speed of the car. So this is how we use the gradient of our distance time graph to find the speed. It is the same as using the speed equation, just dividing the distance with time, and we get speed. So anyways, now that we've understood distance time graphs and understood all the different kinds of graphs, we can move ahead onto speed time graphs. So in a speed time graph, if the graph is a straight line like this one here, it means that the speed is increasing at a constant rate. So the car is accelerating but at a constant rate. So this is called a uniform acceleration. In distance time graphs, this kind of graph, which is a straight line, was supposed to be explaining constant speed in distance time graphs. But in speed time graphs, this explains a uniform acceleration. And it can also be shown a uniform deceleration if the graph starts from here and ends here as a straight line. But if a speed time graph is curved, then the acceleration is not constant. It is not a uniform acceleration. So a curved speed time graph would be a non-uniform acceleration or deceleration. But in speed time graph, if the graph is a horizontal line, it would mean that the speed is constant. It is neither increasing or decreasing. So this type of graph in a speed time graph would be called a constant speed. Otherwise, in distance time graphs, this type of graph is called no movement at all. It is a stagnant. So it is like if a car has stopped, because that is the distance time graph. So speed time graph is different from distance time graphs. So if a speed time graph is like this, a horizontal line, this means that the time is increasing and the car is moving, but the speed is not changing. So the speed is constant, which is 40. In distance time graphs, the constant speed graph is something like this. It is a straight line. So this means that the speed is constant. It is not increasing or decreasing, but it is constant. And in a speed time graph, it is a horizontal line. And a straight line in speed time graphs refers to a uniform acceleration. It means that the speed is increasing at a constant rate. So, on a speed time graph, the gradient of the line is numerically equal to the acceleration. By gradient, we mean this part of the graph. This is numerically equal to the acceleration. So what it basically means, the speed divided by time, the gradient of the line is numerically equal to the acceleration. So basically, if it is a horizontal graph like this, there is no acceleration. If it is a graph like this, there is a uniform acceleration. And if such a graph is curved in shape, then it is a non-uniform acceleration. Now, on a speed time graph, the area under the line is numerically equal to the distance traveled. By area under the line, we mean the speed and the time. So to find distance, we multiply speed with time and we find the distance. So if a graph is like this and the speed is not increasing or decreasing, we would simply multiply 40 by 11 to find the distance traveled. But if the graph is something like this, then we would multiply 90 by 11, just like we did with this, and then divide it by 2. So basically half in the value. So we find the distance traveled. So this is how we find the distance using speed time graph as well. Remember, the equation of speed always applies in these places. The equation is rearranged in this case to find distance. So distance is equal to speed into time, and speed is equal to distance divided by time. So this is what speed time graphs are. So the difference between distance time graphs and speed time graphs, I hope, are very clear now, because they can be a little confusing. For me, they were very confusing in the beginning, but now I've understood, because the shapes are similar to each other, but they mean different things. So on a distance time graph, such a shape means that there is a constant speed, that the speed is not increasing at all. And if you want to represent constant speed in speed time graphs, we will make a horizontal graph. And if a horizontal graph is in distance time graphs, this would mean that there is no motion at all, that the car is not moving at all. And a distance time graph like this, which has a curved path, means the car is accelerating. So over here we do not know whether the acceleration is uniform or not uniform. So the car is accelerating. By acceleration we mean that it is not constant in speed. So the distance is not increasing at a constant rate. And if such a graph is in a speed time graph, then it would basically describe a non-uniform acceleration. A uniform acceleration is this graph. No acceleration is this graph. A non-uniform acceleration is a graph which has a curved path. So a car is traveling along a straight road. If it has a uniform acceleration, this means that its acceleration is steady, constant. So in other words, it is gaining velocity at a steady rate. If acceleration is not steady, then it is non-uniform, with something like this. This is called a non-uniform acceleration. If the acceleration was steady, then the graph would be a straight line. A stone is dropped from a great height with no air resistance. The velocity time graph for the stone will be like this. So the acceleration would be uniform. It would be 10 meters per second square, which is the acceleration of free fall. So the acceleration is constant. It is increasing, but it is uniformly increasing. But in practice, there is air resistance on the stone, and this affects its motion, producing a non-uniform acceleration like this. This means that its initial acceleration is g because there is not yet any air resistance on it. However, as the velocity increases, air resistance also increases. So the graph becomes curved in shape. On a speed time graph, the area under the line is numerically equal to the distance traveled. So this applies whether the motion is uniform or non-uniform. In other words, whether the graph line is straight or curved. With a straight line graph, the area can be calculated. But with a curved line, this may not be possible, although an estimate can be made by counting squares. When doing this, remember that the area must be worked out using the scale numbers on the axis. It isn't the real area on the paper. Now that we've understood graphs, let's move ahead onto understanding the motion of objects. So, using the ticker tape timer. What is a ticker tape timer? The ticker tape timer is also another way to record motion. In the ticker tape timer, we have a paper tape. The paper tape is either pulled by hand or attached to a trolley on a slope so that it moves towards the bottom and pulls the tape. So the paper tape is either pulled by hand or attached to a trolley on a slope so that it moves down towards the bottom and pulls the tape. So when the paper tape is pulled, it passes through a ticker tape timer which punches carbon dots on the tape at regular intervals. Together, the dots on the tape form a complete record of the motion of the trolley. The further apart the dots, the faster the trolley is moving. So here we have some examples of these. So this one shows a constant speed but a fast speed. So as you can see, in this one we have some closer dots over here and the dots just get further apart as it moves over here. So this is an example of acceleration. Trolley speeds has increased. And this one is also an example because the dots are so close over here at this point, and as it moves along, they get further and further away from each other. So the speed is increasing. So if the tape is chopped up into 5 or 4 dot space sections, and the sections are put side by side in order, like this, the result is a chart like this one. The chart is the shape of a speed time graph. So the lengths of the sections represent speeds because the trolley travels further in each second as its speed increases. Side by side, the sections provide a time scale because each section starts 1 second after the one before. The acceleration of the trolley can be found from measurements on the tape. This is how we use the ticker tape timer to record the motion of a trolley. Now let's move ahead onto understanding free fall. So, if you drop a lead weight and a feather, both fall downwards because of gravity. However, the feather is slowed much more by the air. So, if there were no air resistance, both objects would fall with the same downward acceleration, which is 9.8 meters per second square. And this is called the acceleration of free fall. It is the same for all objects falling near the Earth's surface, light and heavy alike. So, a light object, like a feather, can trap more air because it is light. So light objects trap more air, that's why the feather would be slowed much more compared to a lead weight. But if there is no air resistance, any object, whether it is heavy or light, would fall with the same downward acceleration, which is 9.8 meter per second square. This is the acceleration of free fall, and it is the same for any object falling near the Earth's surface, light and heavy alike. So the acceleration of free fall is represented by the symbol g. The value of g near the Earth's surface is close to 10 meter per second. This is also called the gravitational field strength of Earth. Now let's understand how we can measure g. So an experiment to find g is as follows. The principle is to measure the time taken for a steel ball to drop through a known height and to calculate the acceleration from this. So the air resistance has little effect on a small heavy ball falling only a short distance. So the ball's acceleration is effectively g. So the apparatus is made where there are two light beams, one at the starting from where the ball is going to be falling and one at the end where the ball is going to hit the ground. There is an electromagnet that is holding the ball. So when the power to the electromagnet is cut, the ball is dropped. And the electronic timer is automatically switched on when the ball passes through the upper light beam and switched off when it passes through the lower beam. So if the height of the fall is h and the time is taken as t, then g can be calculated using this equation. G is equal to 2h upon time square. So 2 multiplied by the height of the fall divided by t square, which means if we multiply the time by itself twice. So when 2h is divided by t square, we get g. So now let's look at this example over here. Assume that g is equal to 10 meter per second square and that there is no air resistance. So as an upward velocity of 30 meter per second is the same as the downward velocity of minus 30 meter per second, the motion of this ball can be described like this. So when it is thrown upwards at 0 seconds, the downward velocity is minus 30 meter per second. And after 1 second, the downward velocity increases. So it becomes minus 20 meter per second. After 3 seconds, it increases to minus 10 meter per second. And after 3 seconds, it reaches 0 meter per second. Then after 4 seconds, it becomes 10 meter per second. 5 seconds, 20 meter per second. And 6 seconds, it comes to 30 meter per second. So the thing is that whether the ball is traveling up or down, it is gaining downward velocity at the rate of 10 meters per second. So it always has a downward acceleration of 10 meter per second square, which is g. Even when the ball is moving upwards or is stationary at its highest point, it still has downward acceleration. So this is what this experiment is telling us, that the ball or any object or anything always has a downward velocity, which is basically the Earth's gravitational field strength, which we call g. So g is the downward velocity of Earth. So because the gravitational field strength has a force on us, we always have a downward acceleration or velocity of 10 meter per second square, which is also called g. So now that we've understood free fall, let's move ahead onto forces and balance. So a force is a pull or push exerted by one object on another. It has a direction as well as magnitude, so it's a vector quantity. The SI unit of force is the Newton, and we use a spring balance to measure force. Small forces can be measured using a spring balance like this one. The greater the force, the more the spring is stretched and the higher the reading on the scale. So here I have some common examples of forces. First we have frictional force, then we have gravity, magnetic force, applied force, the upthrust of water, this is also a force, the weight of the boat, it's also a force, tension force, which is also called elastic force, the drag force, also called air resistance, and the spring force, the force which is in springs. So these are some examples and types of forces. On Earth, unpowered vehicles soon come to rest because of friction. But with no friction, gravity, or any other external force on it, a moving object will keep moving forever at a steady speed in a straight line. It doesn't need a force to keep it moving. This idea is summed up in a law first put forward by Sir Isaac Newton in 1687, known as Newton's first law of motion. The law states that if no external force is acting on it, an object will, if stationary, remain stationary, and if moving, will keep moving at a steady speed in a straight line. This is known as Newton's first law. Now let's look at some balanced forces. This law will come into them as well. So an object may have several forces on it, but if the forces are in balance, they cancel each other out. Then the object behaves as if there is no force on it at all. So as you can see, this gymnast has balanced herself on this beam nicely. So because she is balanced, there is no force acting on her at all. As Newton's first law states, if no external force is acting on it, an object will, if stationary, remain stationary. So this rule applies over her because as she is stationary, she will remain stationary in this position. And ice skaters make use of this law as well, because when they skate, they balance themselves at a position where the forces cancel each other out. And if they are moving, they will keep moving at a steady speed in a straight line. This is how ice skaters keep moving even when they are not moving their body at all, or they have a same position, they are still moving on the ice. So Newton's first law of motion is the reason of all of this. That if no external force is acting on it, an object will, if stationary, remain stationary, and if moving, keep moving at a steady speed in a straight line. Now let's look at terminal velocity. So when a skydiver falls from a hovering helicopter, as her speed increases, the air resistance on her also increases. Eventually, it is enough to balance her weight and she gains no more speed. She is at her terminal velocity. So basically, her weight and the air resistance cancel each other out when they become equal to each other. So they cancel each other out and she gains no more speed. So she is at her terminal velocity. But when the skydiver opens her parachute, the extra area of the material increases the air resistance and she loses speed rapidly until the forces are again in balance at a greatly reduced terminal velocity. So I know there might be many questions coming in the mind. Say for example, if air resistance balances her weight, why doesn't a skydiver stay still? Because if she wasn't moving, there wouldn't be any air resistance. And with only her weight acting, she would gain velocity. So the Newton's law states that if no force is acting on it, an object which is moving will keep moving at a steady speed in a straight line. And if an object is stationary, then it will remain stationary. So another question, surely if she is traveling downwards, her weight must be greater than the air resistance. That is only if she is gaining velocity. At a steady velocity, the forces must be in balance, and that follows from Newton's first law. So this was terminal velocity. Pretty simple, right? Now we can move ahead on to inertia and mass. So all objects resist a change in velocity, even if the velocity is zero. So this resistance to change in velocity is called inertia. And the more mass something has, the more inertia it has. Any change in velocity is an acceleration. So the more mass something has, the more difficult it is to make it accelerate. So what we're saying here is that every object resists a change in motion or a change in velocity. Both are the same thing. Just like we read in the measurements and units when I was explaining about mass, the point to note there was that the more mass something has, that object would have more resistance to change in motion. So basically what that means is that the more mass something has, the more inertia it has. So inertia is the resistance to change in velocity or in motion. So any change in motion is an acceleration. The more mass something has, the more difficult it is to make it accelerate. Now, as you can see in this diagram, there are two forces which are unbalanced. So the ball has a force at this direction which is 3 Newton and a force in this direction which is 5 Newton. So they are unbalanced forces. This force is greater than this one. So together they are equivalent to a single force, and which is called the resultant force. So when we minus 3 Newton by 5 Newton, we get 2 Newton onto this side because there is more force on this side. So this 2 Newton force is the resultant force on this object. But if the forces are balanced, the resultant force is 0 and there is no acceleration. So any other resultant force causes acceleration in the same direction as the resultant force. So the resultant force is the reason of motion or acceleration. If the forces are balanced, there is no resultant force and there is no acceleration. So here we are on linking force, mass and acceleration. So if the resultant force is 1 Newton acting on 1 kg, then the acceleration is 1 meter per second squared. If the resultant force is 2 Newton acting on 2 kg, then its acceleration is 1 meter per second squared. If the resultant force is 4 Newton acting on 2 kg, then the acceleration is 2 meter per second squared. And if the resultant force is 6 Newton on 2 kg, then the acceleration is 3 meter per second squared. So in all cases, this equation applies, that resultant force is equal to mass into acceleration, also known as F is equal to ma. So this is the equation of force. Any kind of force can be measured with this equation. So this relationship between force, mass and acceleration is sometimes called Newton's second law of motion. So let's do a question using this equation. Here we have a car and the question is, what is the acceleration of this car? So let's look at it first. We have an 18 Newton force of the engine of the car and a 10 Newton total frictional force, which is the backward force. The mass of this car is 2 kg. So first, to find out the acceleration, we need to work out the resultant force on this car. So of course the resultant force is pretty simple to find because the force on this side is greater than the force on this side. So we minus this force from this one to find the resultant force, which is 8 newtons to the right because this side has more force. So the resultant force is to the right. That is why the car is moving in that position, because the force from the motor is more than the total frictional force. That is why the car is moving in that direction. So the resultant force is 8 Newton in that direction. Next we work out the acceleration when force is equal to 8 newtons and mass is equal to 2 kg. So we apply the force is equal to ma equation and substitute the values. So we get 8 is equal to 2a. 8 is the force and 2 is the mass, and so we basically rearrange this equation to find the acceleration. How can we rearrange the equation? It's pretty simple. So force is equal to ma. Force will go on top and m and to a is at the bottom. We can again use the triangle method. If you want to find the a, we basically hide the a, and what you get is force upon m. If you want to find m, we hide the m, and what we get is force upon a. So it's pretty simple. So to find a, we divide force by m. So we divide 8 by 2, and what we get is 4. So the car's acceleration is 4 meter per second square. So this is how we use this equation to find the acceleration of objects. And the resultant force equation is also used over here, as you saw. We found the resultant force as well of the car. So forces do not only affect motion. If 2 or more forces act on something, they change its shape or volume or both. The effect is slight with hard objects but be very noticeable with flexible ones. Okay, so now let's look at the two kinds of friction. So, to explain this experiment is done. When a block is pulled gently, friction stops it moving. As the force is increased, the friction rises until the block is about to slip. This is the starting or static friction. So with a greater downward force on the block, the static friction is higher. Once the block starts to slide, the friction drops. Moving or dynamic friction is less than static friction. So these are the two kinds of friction: static friction and dynamic friction. Static friction is when an object which is stationary is pulled. So at that time the friction is more, it is greater, because the downward force on the block is greater. So the static friction is higher. But once the block starts to slide, the friction drops. Moving or dynamic friction is less than static friction. So these were the two kinds of friction. Now let's look at drag. Drag is also called air resistance. But it is not only air resistance. Objects experience friction when they move through a liquid or gas, and this force is called drag. So the upthrust force we feel when we are in water is also a drag force. So it is a force that occurs in a liquid or gas. Air resistance is an example of drag, and upthrust of water is an example of drag. So gravitational force, which is also called gravitational field strength, which we also call G, is the downward pull from the earth, which keeps us standing on the ground. So if you hang an object from a spring balance, you measure a downward pull from the earth, and this pull is called a gravitational force. So these are the points to remember about gravitational force. Firstly, all masses attract each other. So anything that has mass and volume would be attracted to the gravitational force of Earth. The greater the mass is, the stronger the force. Basically, mass is directly proportional with the gravitational force. So if mass increases, the force also increases. If mass decreases, the force also decreases. The closer the mass is, the stronger the force. By this we mean that the denser the object, the stronger the force. So if an object like solids have closer masses or perhaps more mass than gases or liquids, so solids have a stronger force of gravity. So there is a stronger force of gravity on solids compared to liquids and gases, because solids are denser than the liquids or gases. So the closer the masses, the stronger the force. So weight is another name for the Earth's gravitational force on an object. Like other forces, it is measured in newtons. Now, near the Earth's surface, an object of mass 1 kg has a weight of 10 newton. So greater masses have greater weights. So here we are on weight now. Of course, in normal life we measure weight in kgs, but in physics we measure weight in newtons, as it is a force. Weight is not the mass of an object. Weight is the Earth's gravitational force on an object. To measure weight, we use spring balances. A spring balance is something with which you hang an object. So when the object hangs with the spring balance, it measures the downward pull of Earth on the object. So if it's a light object, then it would have less weight, and so the pull would be less. So that is how we use a spring balance to measure a downward pull of Earth. And weight in physics is measured in newtons. Weight is a force in physics. So near the Earth's surface, an object of mass 1 kg would have a weight of 10 newtons. The greater the mass is, the greater the weights are. So weight is kind of like another name for the Earth's gravitational force on an object. Okay, now let's look at the gravitational field strength, something that I have been talking about in this chapter quite a lot. So a gravitational field is a region in which a mass experiences a force due to gravitational attraction. The Earth's gravitational field strength is 10 newtons per kilograms, which is Newton per kg. So gravitational field strength is also denoted as G. G has, in other words, two meanings. G is the acceleration of free fall as well as the gravitational field strength, which is 10 Newton per kg. So this is the equation we use to measure weight, or in other words, to measure the gravitational force of Earth. Weight is equal to mass into G. G is the gravitational field strength. So gravitational field strength is 10 Newton per kg, whereas the acceleration of free fall is 10 meter per second square. So that is acceleration. Don't confuse that with this, because this is a force. That is acceleration. So G has, in other words, two meanings. One is the acceleration and the other is the gravitational field strength. Okay, now let's do a question here. The question is, what is the acceleration of the rocket? Okay, this is a rocket. As you can see, the rocket has a mass of 200 kg. And the force from the rocket's engine is 3000 newtons. The weight is not given. But they're not actually asking us for the weight. They're asking us what is the acceleration of the rocket. So to find the acceleration, you need to know the resultant force on the rocket. And to find that, you need to know the rocket's weight. Because to find the resultant force, we need to minus the downward force from the upward force, as it is bigger. And the downward force of the rocket is its weight. But we don't know the value of the weight, so we're going to measure it like this. Weight is equal to mg, so the mass of the rocket is 200 kg and the gravitational force is 10 Newton per kg, always. So when these two get multiplied, and so the weight of the rocket is 2000 Newton. So now that we found the weight of the rocket, we can find the resultant force. So the downward force is 2000 and the upward force is 3000. So 2000 minus 3000 and we get 1000 newtons. So 1000 Newton is the resultant force of the rocket in the upwards direction. Now we are going to find the acceleration of the rocket, and for that we're going to use this equation. Force is equal to ma. So we get the resultant force, which is 1000 Newton, equal to 200 kg into acceleration. When we rearrange this equation, which is to find acceleration, we divide the resultant force with mass and we get 5 meter per second square. So the acceleration of this rocket is 5 meter per second square. So which equation are we going to use in which questions depends on what the question is handing over. So this question, for example, had given us the mass and the force and the weight of the rocket and wanted us to find the acceleration of the rocket. Now in this situation, we're not going to apply the acceleration is equal to change in velocity upon time taken equation, because we're not given the change in velocity over here. Instead, we're given the mass and the force of the rocket. So we're going to find the resultant force. Why are we going to find the resultant force? Because we're going to apply this equation here. To find the resultant force, we had to find the downward force as well, which is the weight. So we then first find the weight, then we find the resultant force, and then using this equation and the resultant force, we find the acceleration. So this is how we use different equations. The question is asking for acceleration, then it is not necessary that only the acceleration equation would be used over here. The resultant force equation is used over here instead, because it can be rearranged and be used to find acceleration as well. So now that we've understood the gravitational field strength, the gravitational force, weight, and all the g forces, we can move ahead on to understanding weight and mass. So on the moon, your weight in newtons would be less than on Earth, because the moon's gravitational field strength varies. Moving away from the Earth, your weight decreases. If you go deep into space and free of any gravitational pull, your weight will be 0. Just like I was talking about this in the first chapter of measurements in units, when I was talking about mass, that mass is always fixed, whereas the weight changes. So whether on Earth or moon or deep into space, your body always has the same resistance to change in motion, which means your mass in kg doesn't change. So, as we all know, in space, we don't have any force acting on us. The force that would be acting on us when we are on Earth is the gravitational force. That is our weight which acts. But when we go deep into space, our weight changes and it becomes zero. When we go on the moon, the weight changes and becomes less than on Earth because the moon's gravitational field strength varies. So our weight can change because of the gravitational field strength that acts on us. But the mass of our body never changes. The mass is always fixed. So our body always has the same resistance to change in motion. Now let's understand and clear the two meanings for g. The acceleration of any object can be worked out using the equation force is equal to mass into acceleration, just like we did over here in this rocket example, rocket question. So for example, the 2 kg mass has a 20 Newton force on it. So its acceleration is going to be 10 meter per second square. So you get the same result for all other objects. In each case, the acceleration works out at 10 meter per second square, or g. So g has two meanings. In both cases, g is a vector. By vector, we mean something that has magnitude as well as direction. So the two meanings for g are, g is the gravitational field strength, which is 10 newtons per kilograms. And the second is that g is the acceleration of free fall, 10 meter per second square. So I had already cleared this out, but right now we have it in written form here. And so it is very important for us to understand the two meanings for g so that we don't confuse them up. G can also be called the gravitational field strength, which is 10 Newton per kilograms. No matter if the object is heavy or light, the gravitational field strength would be 10 Newton per kilograms. And g is also the acceleration of free fall, which is 10 meter per second square. And this this acceleration of free fall also acts on any kind of object, whether it is light or heavy, whether it is light or heavy. But the acceleration of free fall changes if air resistance comes in. So with no air resistance, it will remain the same for any kind of object. So these were the two meanings for g. Now that we've understood the difference between weight and mass and the two meanings for g, we can move ahead on to understanding action and reaction. So here we are on action and reaction. Let's understand it. A single force cannot exist by itself. Forces are always pushes or pulls between two objects, so they always occur in pairs. So, for example, this diagram shows that when the piston between these two trolleys is released, the trolleys shoot off in opposite directions. So, two equal but opposite forces are produced, one acting on each trolley. The paired forces are known as the action and the reaction. So, reaction. But it doesn't matter which you call which. One cannot exist without the other. Now, again, this might also have many questions. Say, for example, if forces always occur in pairs, why don't they cancel each other out? So, the answer to this question is that if the forces in each pair act on different objects, not the same object. So as you saw over here, there were two trolleys. One force acted on one trolley and the other acted on the other trolley. So they were not acting on a single trolley. Each trolley has its own force. That is why they didn't cancel each other out. If there is only one object on which the forces are applied, then they would cancel each other out. So as it is said over here as well, that forces are always pushes or pulls between two objects, not a single object. Okay, the second question is that if a skydiver is pulled downwards, why isn't the Earth pulled upwards? Well, the Earth is pulled upwards, but the Earth is so massive that the upward force on it has far too small an effect for any movement to be detected. This is a complete different thing, but let's understand that if object A exerts a force on object B, then object B will exert an equal but opposite force on object A. So, to every action, there is an equal but opposite reaction. And this is known as Newton's third law of motion. To every action, there is an equal but opposite reaction. Equal but opposite reaction, remember. And the objects are always two. There is not a single object. If two equal but opposite forces act on a single object, they would obviously cancel each other out. Okay, now that we understood action and reaction, we can move ahead onto momentum. So momentum is equal to mass into velocity. P is equal to mv. P is known as momentum, m as mass, and v as velocity, of course. For example, if a model car has a mass of 2 kg and a velocity of 3 meters per second, its momentum will be 2 kg into 3 meters per second equal to 6 kg meter per second. Note that the unit of moment is kg meter per second. So like velocity, momentum is a vector quantity as well. So a plus sign or minus sign is often used to indicate its direction. Now we're going to be learning more about momentum and turning forces in the second chapter. But for now, this is what momentum is. The equation is what matters the most. So momentum is equal to mass into velocity. Newton's second law of motion. With the resultant force on it, an object will accelerate. This was Newton's second law. We had read it before. Therefore, its velocity will change, and so will its momentum. Now, this is a new piece of information that when velocity changes, momentum also changes. So, an object accelerates when a resultant force acts on it. Basically, when the forces on an object are not equal to each other. So, there is a resultant force on an object and the object accelerates. Therefore, the object's velocity changes and so does its momentum. So the force and the momentum change are linked by this equation. The equation is resultant force is equal to change in momentum divided by time. So the link between a resultant force and the rate of change of momentum it produces is known as Newton's second law of motion. Newton's second law of motion also states that with the resultant force on it, an object will accelerate. But Newton's second law also states that when the velocity changes, the momentum also changes. And the change of momentum and velocity is linked by this equation. So resultant force is equal to change in momentum upon time. Now we have 3 different equations to use to find resultant force. As you can see, this also can be used to find resultant force. Force is equal to ma equation is also used to find the resultant force. And larger force minus smaller force is also an equation we use to find the resultant force on an object. So these are different equations that can be used in different scenarios. Now speaking of scenarios, let's do a question over here. So, a model car of mass 2 kg is traveling in a straight line. If its velocity increases from 3 meters per second to 9 meters per second in 4 seconds, what is the resultant force on it? So to begin finding the answer, we use this equation. Momentum is equal to mass into velocity. We have read this equation when we were understanding momentum. So momentum is equal to mass into velocity. We have mass here and velocity, and the first velocity, which is 3 meters per second. So when these two are multiplied, we get 6 kg meter per second, which is the momentum. And after 4 seconds, the velocity changes to 9 meters per second. And so when we multiply 9 meters per second by 2 kg, we get 18 kg meter per second. So change in momentum is 12 kg meter per second. What we did was minus 6 kg meter per second by 18 kg meter per second to find the change in momentum. So the change in momentum is 12 kg meter per second. This is how we find the change in momentum, and now we use this change in momentum to find the resultant force. So the resultant force is equal to change in momentum divided by time. The time was 4 seconds. So change in momentum occurred in 4 seconds. So 12 kg divided by 4 seconds, and we get the resultant force, which is equal to 3 Newton. So this is how we use this equation as well as the momentum equation to find the resultant force of this object. Now it is interesting to solve questions like these. Let's do another one. So the question is, a small rocket pushes out 2 kg of exhaust gas every second at a velocity of 100 meters per second. What thrust force is produced by the engine? By thrust force, we mean the upward force on the rocket. By Newton's third law of motion, the forward force on the engine is equal to the backward force pushing out the exhaust gas. That force can be calculated by finding the rate of change of momentum of the gas. In 1 second, 2 kg of gas increases its velocity from 0 to 100 meters per second. So the change in momentum is again mass is equal to velocity change. How do we find the velocity change? We minus the old value by the initial value. So the change in momentum is mass into velocity, and we get 200 kg meter per second. Now we again use the force is equal to change in momentum upon time equation to find the force on the engine. So the force on the gas is equal to change in momentum divided by time, and we get 200 divided by 1 second, and we get 200 Newton. So the thrust is equal to 200 Newton. So these two questions, I hope, were very clear to understand. So as you saw, these two equations are used in such scenarios. So here we have another experiment, or in other words, question. So to begin with, the trolleys are stationary. This trolley has mass 2 kg and this one has 4 kg mass. So when the rubber band is cut, they shoot off in opposite direction. This is the rubber band. Their velocities can be measured using ticker tape timers. So when the trolleys shoot apart, the trolley with the least mass has the most velocity. So the diagram shows typical mass and velocity values, but mass into velocity to the left is equal to the mass into velocity to the right. So the momentum of each trolley is the same, is equal to each other. So, well, the result is to be expected. From Newton's third law of motion, the forces on the two trolleys are equal but opposite. Also, the forces act for the same time, so they should cause equal but opposite changes in momentum. So as you saw, this trolley had 2 kg mass and the speed of it was 1 meter per second. And this trolley had a mass of 4 kg and its speed was 0.5 meter per second. But when we multiply the two values and find the momentum, they are equal, 2 kg meter per second, except for that they are in the opposite direction. So by Newton's third law, the result is to be expected because it states that the forces on the two trolleys are supposed to be equal but opposite in direction. So also the forces act for the same time, so they should cause equal but opposite changes in momentum. So the change in momentum should be also equal but opposite in direction. Okay, with the mass and velocity values, the total momentum of the trolleys before and after separation can be found. As the momentum is a vector, its direction must be allowed for. So before the spring is released, the total momentum of trolleys was 0. After the spring was released, the momentum of trolley A, mass into velocity, becomes minus 2 kg meter per second. And the momentum of trolley B becomes plus 2 kg meter per second. So the total momentum of trolleys is 0. So the total momentum is unchanged by the release of the spring. This is an example of the law of conservation of momentum. Now that we've understood this action and reaction again using this question, we can move ahead onto understanding vectors and scalars. So quantities such as force, which have a direction as well as a magnitude, are called vectors. We have read this before, we have understood this. So two vectors acting at a point can be replaced by a single vector with the same effect. This is their resultant. So finding the resultant of two or more vectors is called adding the vectors. Now this is something different. Two vectors acting at one particular point can be replaced by a single vector with the same effect. This is basically their resultant force. So when we are finding the resultant force of two or more vectors, we call it adding the vectors. So quantities such as mass and volume, which have magnitude but no direction, are called scalars, scalar quantities. Adding scalars is easy. So for example, a 30 kg block is placed on a 40 kg block. So the total mass of both the blocks would be 70 kg. Pretty simple. But to find the resultant of two vectors is a little tricky. So to find the value of the resultant, we use the Parallelogram Rule. As you can see in this diagram, the ship is being pulled forward by the resultant of the forces from these two tugs. Even though they are in opposite directions, but they are equal. So when two vector quantities are acting at a point, they can be replaced by a single vector with the same effect, which would be in the middle, coming in the middle. So when these two tugs are opposite but equal directions, the boat moves forward in a straight line, like this. This is the direction of the boat. So these two tugs can be replaced by a single force in this direction as well, but it would need more force to do so. Right now there are two boats taking it. It would need one big ship to move this big ship as well. Anyways, the parallelogram rule is a method of finding the resultant in situations like this, where the vectors are not in line. So it works like this. This is the method of the parallelogram rule. First, we draw two lines on a paper from O to represent the vectors. O is going to be the ship. The directions must be accurate and the length of each line must be in proportion to the magnitude of each vector. Draw in two more lines to complete a parallelogram rule. So for example, there is an object on which there is a force acting of 30 Newton in this direction and a force of 40 Newton acting in this direction. So basically, if we make 1 millimeter equal to 1 Newton of force, then we would make 40 millimeters over here and 30 millimeters over here and add two more lines to make the complete parallelogram. We're going to draw a diagonal line from O and measure its length. So the diagonal will represent the resultant in both magnitude and direction. So if the direction of force 30 Newton is this and force 40 Newton is this, the resultant force direction would be this. Just like in this situation, when we would make a parallelogram and make a diagonal line in between, we would get the direction which would be this. And we can also find the magnitude as well by measuring it. So if 1 millimeter is equal to 1 Newton, we would measure how much millimeters is the length of this resultant force and we will find it. So the millimeters are 60. So the resultant force is going to be 60 newtons. So this parallelogram rule also works in reverse. A single vector can also be replaced by two vectors having the same effect. Scientifically speaking, a single vector can be resolved into two components. When using the rule in this way, the single vector forms the diagonal. So then the single vector would be the diagonal line in the parallelogram. Okay, so this was the parallelogram rule that we use to add two vectors together. It is pretty simple as you saw. Now we're going to understand the centripetal force. Okay, so someone is whirling a ball around in a horizontal circle at a steady speed. An inward force is needed to make the ball follow a circular path. The tension in this string provides this force. Without it, the ball would travel in a straight line as predicted by Newton's first law of motion. And this is exactly what happens if the string breaks. It goes off in another direction in a straight line. So, the inward force is supposed to be in the center of the circular path of the ball. So the inward force needed to make an object move in a circle is called the centripetal force. More centripetal force is needed if the mass of the object is increased. And more centripetal force is also needed if the speed of the object is increased. And also if the radius of the circle is reduced. So more centripetal force is needed if the mass is increased, and if the speed is increased, and if the radius of the circle is reduced. Now let's look at some examples of the centripetal forces. The first example is orbits. So, example of orbits is satellites around the Earth and the many different planets around the Sun. Anyways, let's start with satellites around the Earth. A satellite travels the Earth in a curved path called an orbit. This is an orbit. Gravitational pull, in other words the satellite's weight, provides the centripetal force needed. Centripetal force is always in the direction of the center of the circle. So in this case, the orbit's center is the Earth basically. So this is the center, and this is where the force is. So if the object is over here, the force would be in this direction. If it is over here, it would be in this direction, here, then in this direction. So this is the direction of the centripetal force, always inwards. The second, we have planets around the Sun. This is also an example of orbits. The Earth and other planets move in approximately circular paths around the Sun. The centripetal force needed is supplied by the Sun's gravitational pull. So as you can see, Mercury also has its own orbit, Venus also has its own orbit, Earth, Mars, Jupiter, Saturn, and Uranus, they all have also this asteroid belt. They are all in their own orbits around the Sun, and the centripetal force is the Sun's gravitational force basically. And the last example we have are electrons around the nucleus of an atom. So in atoms, negatively charged particles called electrons are in their orbit around a positively charged nucleus. This is the nucleus, and these are the electrons which have their own orbit. The attraction between opposite charges provides the centripetal force. So because negative gets attracted to positive, that is the reason of the centripetal force of atoms. Examples of centripetal force also includes when a car is turning a corner, say for example. It also has a centripetal force in the center of the circular motion. So this was the second chapter of our physics O-level lessons. Today's lessons was a very big lesson and a very interesting one. It includes many different equations, many different laws of motion, many different questions we did using these equations, and many different kind of forces that we understood. We understood friction, we understood drag, and we understood Newton's laws as well. We understood how forces get cancelled when they are balanced. And in the beginning of the chapter, we understood acceleration, speed, and velocity, and how we use different equations to find them, and how we use graphs to find them, and how distance-time graphs differ from speed-time graphs, and their shapes differ from each other, and what their shapes mean, basically. How we solve different problems using the equations we learned, such as the equation of acceleration and the equation of velocity and of speed. So this was all about forces and motion. We've covered all the topics in this chapter in detail and have done questions related to it. So I hope this was an interesting and fun chapter for you, and you will memorize all the equations and all the different laws of motion. And so next chapter is going to be forces and pressure. Thanks for watching this video. See you in the next chapter.